Hey guys, it's Cade from All Systems Go, and today we're going to do a brief little explanation of our linear indexing robot HOTLINE that we competed with at our league meet, states, and the Governor's Cup where we placed third. So first of all, what is a linear indexer? That was something that we had the idea for on day one, and it's the idea of moving your launching mechanism back and forth so that you don't have to move the balls. And it was a little crazy. We were kind of inspired by RoboKing's Aurum from Center Stage and just how awesome that robot was. And so we wanted to do something out of the box and unique. So this whole turret slides back and forth on these linear rails right here. And that allows us to, when we intake the balls in a straight line, we can effectively select which ball we want to shoot. So this is powered by a differential which has two Axon Max servos. And you can kind of see them, one down here and one in here. And so these servos power these spools right here that when they spin in the same direction, it slides back and forth, allowing us to select which ball we want. And when they spin in the opposite direction, that gives us that shooting capability of being able to shoot from anywhere on the field with that rotating turret. And this was a big thing. We wanted to be able to sort, we wanted to have that capability, but we didn't want to sacrifice our intaking speed or our firing speed or the capabilities of being able to shoot with that turret. And so we wanted to be just as good as any pass-through robot out on the field while still having that capability to get those motif points. So when we were thinking about it strategy-wise, the one thing we didn't want to compromise on was our shooting speed, as we mentioned before, or our intaking speed. And that's because the sorting really only matters in auto and at the end of teleop, and for the rest of that, you're just effectively spamming as many balls into the goal as you can. And so for our intake, one of the key things here was that it's powered by two motors, and it also serves as our indexing system for when we bring the balls back. So these two bare motors, which are down here, you can see them right here, they power belts that come up to here and power this main shaft, which is custom molded silicone gecko wheels on it. And this then runs through these miter gears right here, which power the side rollers. And that was just something unique and innovative we didn't see too many teams trying out. And we really wanted to improve our corner balls from the V1. And so that helped a lot in competition. We were able to get out of the corner those balls really quickly. From there, these vectoring belts help when we're up against a wall and we're pushing balls. It'll help vector them inwards, gives it a little bit of compression and compliance too. And then that belt powers this long HTD3 belt back here, which runs the balls to the rear of the robot. From there, that shaft also has miter gears on it, and it powers these gecko wheels right here, which help launch the balls into the turret. And one thing that's pretty unique about this robot too is the sorting system has these three flickers, so we can select ball number 1, ball number 2, or ball number 3. And the key thing about this is that the flicker for number 3 is a slope. You can see it has this kind of a triangle architecture here, and that is what gave us the ability to have 0.35 second rapid fire, putting us on par with everybody else out there on the field. So when we run the intake, obviously the belt is running all the balls back. When they hit this back one, simultaneously they'll get launched up into the shooter because of these gecko wheels back here as well. Next up is our turreted shooter. So as we mentioned before, powered by the differential, this is the second axis that we can control, and it's in servo mode actually, so we didn't need to tune PID or do any shenanigans with control theory like that. So a pretty rigid 3D printed PETG frame with some aluminum standoffs at the back hold it together, and this flywheel and the rack and pinion allow us to adjust the speed, so the distance and the arc angle we fire at pretty reliably, and so we just run a regression based off of that for determining that flywheel speed on the field. We have about 12 data points for that. These two bare motors at the back power it. It's pretty standard, nothing too crazy. We run it 1-to-1, and that was a pretty good ratio that we were comfortable with, and we have about 800 grams of flywheel weight here that help us keep up that inertia so we can rapid fire in 0.3 seconds. So next up, let's talk about the drivetrain and the overall structure and design of the robot and how we got here. So starting at League Meet 1, which our first League Meet was really early, it was November 1st, we knew we had to get something out the door pretty quickly, and so we found ourselves running a standard parallel plate drivetrain, HTD5 belts on some 435 RPM motors, belted down to about 360 RPM because our robot was a lot heavier back then. But for this V2, we knew we wanted to keep in line with what we were going for, something crazy, something out of the box, something unique, but also at the same time something that would give us a competitive advantage. And that's what found us running this drivetrain style using all bare motors. And so the way that this drivetrain works is there's a tiny 9-tooth pinion gear on each one of these bare motors down here that goes up to a 108-tooth gear on these wheels right here. We're running the Gobelda 104mm grip forces. We found they work really well. They don't have any rubbing issues on the field. And this gives us a final output ratio of about 485 RPM, which is plenty fast on the field. We're blazingly fast, and so we can escape defense, we can get in and out of the shot zones pretty quickly, and we found that it's a ratio we like and we're planning on keeping. The structure-wise, these are 48mm drivetrain pods, which are more compact than the 56s, and this was kind of a packaging challenge for fitting all of our components inside of there, but it was something that we knew, okay, if we can shave off a half an inch inside that box during endgame, we can potentially fit better with other teams, or if they're doing a tilt, we can have them in there as well, and so we can get those bonuses. And you can see our drivetrain base is also pretty narrow too, and they're not close to the front. So we have more components at the back, and we have more components at the front. So that means we can park in that box pretty comfortably during endgame, and we can actually do a full 360 spin inside that box while remaining in there. So next up, some software and some sensors we have on here. We use 3 color sensors down here. They're just the standard Rev color sensors, and they allow us to detect the colors of the balls in our robot, and so that helps us for auto, that we know which pattern we're going to end up sorting, and for teleop, it shows us the colors on these LEDs. We also have some other modes in which during auto, if we're running it and trying to tune it, we can show diagnostic data on here by showing them red or green depending on if things are going right, or in teleop as well, we can have them blink on and off when the robot's ready to shoot. And it also gives feedback to the gamepad controllers. So when we're driving, when everything's ready to shoot and it's all lined up, the gamepad controller will rumble so that driver can get instant feedback of when he's ready to push the button to shoot. So one final little detail, the weight of the robot, if you're curious, is about 22.5 pounds. So it is a pretty light robot. There's not much to it. The structure is light, aluminum, pocketed on the outside, pocketed on the inside. We removed about 57% of the weight on each one. And the frame as a whole, we're not using any unnecessary U-channels, any unnecessary bracing. It was all determined in CAD beforehand, so we have the optimal strength where we need it, and that weight efficiency throughout the construction. Thank you for watching. If you have any questions about the robot, feel free to reach out to me on Discord. All of our CAD and code are open source, they're public, and so you can access those at any time. We've been really thrilled this season to see how teams have been taking inspiration from our linear indexers so far. It's been exciting to see you guys at competitions, and we look forward to seeing you in the future. Thank you for watching.